All right, hi y'all. We are going to do notes for 515, which it says completing the quadratic web, which what that means is understanding the relationship between a quadratic function's equation. I'll show you real quick. So we've got equations where we're just looking at equations like this. So we've established the quadratic equation always has the variable squared. So if we had something like this, and then we're relating that to tables. So we've been looking at symmetry with tables and graphs. So we're relating all of these things together and going back and forth between all of these. So as we look at these problems, we have six different graphs of parabolas here. Using the graphs and specifically the x-intercepts, we want to try and figure out the equation in factored form, working backwards with those intercepts, and then put it in standard form. And then we can double check. So on the next page, I know you guys have to flip over, but on the top of the next page, we will try and match each graph to one of these equations. Obviously, we only have 6 graphs and 9 equations, so some of these won't be used, but these are at least available so we can check and see if we're on track. So for the first one, and this comes right off of what we were doing in class with the last section, if we know for sure that we've got two x-intercepts, then we can build the factors that we would expect to see in the factored form of the equation. So in graph 1, we've got an x-intercept at -7 and 4. So working backwards to build the factors, if x equals -7, then the factor for that would be, we would just add the 7 back over with x so that it equals 0. And we would get our factored equation of x plus 7 times x minus 4. So if this is factored form and we want the standard form of that equation, then we can just use the area model as a tool to multiply that out. So we are multiplying x plus 7 times x minus 4. And we've got x squared minus 4x plus 7x minus 28. So just by multiplying that out, we can go ahead and put our equation in standard form. So that's going to be x squared. And then we have -4x and positive 7x, or 7x minus 4x. So a total of 3x's, and then minus 28. So again, this is just coming right off of what we did last class. And then we can double check. I'll just slide down and we're looking for a match of what we just did. So we got x squared plus 3x minus 28. And then we see that right here for option B. So that's good news because we did that correctly and we can see that since we found our equation on the next page. So what I would encourage you guys to do at this point is see how many of these graphs you guys can find the equations for on your own. So even pause the video and try and work ahead and see what you can do on your own. And then if you get stuck on any, you can find where I am in the video going over it. So I'll go over all of them, but if you feel like you've got this, then pause the video and fill it out yourself and just kind of test yourself and see how you do. I will say that specifically with graph 3, that might be one you want to actually watch the video and watch me do that one. And graph 4, and then especially graph 6. So you guys are going to see some unique situations that we haven't talked about yet. So you're going to want to watch these few examples that I've underlined there. But other than those, I would encourage you to see what you can do on your own. Like I said, I'm going to work through all of these, so you feel free to just stay with the video. For this next one, we're looking at another parabola with 2 specific intercepts. We've got intercepts at -6 and -4. So building our equation for that, we would add the -6 back over with the x. So we would expect this this equation to have factors x plus 6 times x plus 4. And then again, to multiply that out, we'll just use an area model. and multiply x plus 6 times x plus 4. We get x squared plus 6x plus 4x plus 6 times 4, which is 24. So then when we combine all of those terms, we end up with the quadratic equation x squared plus 6x plus 4x, so a total of 10x plus 24. And then again, we should expect to see that on the next page on the list of quadratic equations. And we see that right here for part E. Okay, this next one is interesting because unlike the first two and the ones we saw last class, this only has one x-intercept. So we've got our x-intercept at -3. So we know to build the equation in factored form, we're going to end up with at least the factor of x plus 3. But it can't just be x plus 3. There's no other x-intercept to build a second factor, but we know if it was just left at x plus 3, that's not a quadratic equation because there's no x squared. So if we just left it like this, we're looking at the equation of a line. So if we look at our options and just kind of reason through which one of these could be the equation for it, I'm hoping you are drawn to x plus 3 squared. So x plus 3 squared is x plus 3 times x plus 3. And that is the equation for this parabola. So when you only have one x-intercept, that means the vertex itself is the x-intercept. And the equation for those graphs is always going to be x plus or minus depending on what the actual intercept is, and then squared. So those are unique graphs because, like I said, the vertex itself is the only x-intercept. So that's where we see x plus 3 squared, and now we know that that's definitely a quadratic function. So to get that equation in standard form, we'll multiply x plus 3 times itself. So x plus 3 times x plus 3. I want to highlight something really important here. X plus 3 squared is not x squared plus 9. So you can't just square the x and square the 3. You do need to go through the steps of using the area model because you're missing a term if all you do is square the x and square the 3. So x squared plus 3x plus another 3x plus 9. So our equation in standard form here would be x squared plus 3x, so plus 6x, and then plus 9. So it's not just the x squared and the 9. You need the 6x in there as well using the area model. Like I already mentioned, we know that this equation is A, which is x plus 3 squared. This one is not on here in standard form. So x squared plus 6x plus 9 isn't one of our options, but x plus 3 squared is. Okay, looking at the next one, this will be a little interesting. It'll feel a little different from the others, but we've got two x-intercepts. So back to kind of what we're used to with these first two equations. So we've got our x-intercepts. This time though, one of our intercepts is at 0. So that's gonna change a little bit about what our function looks like. So we've got x equals 0 and x equals 4. Those are our intercepts, which means in factored form, so I'm going to write it on a post-it because I don't want to put it on the actual paper. But in factored form, what this would mean is we would have y equals x minus 0. So if we're subtracting that 0 times x minus 4. But since x minus 0 is just x, this factored form is just x times x minus 4. So this looks different, but this x right here means that one of its intercepts has to be just at 0 itself. So that's how we get factored form for this one, y equals x times x minus 4. Then when we multiply that to put the equation in standard form, you can look at it two ways. If you are comfortable with distributing, the process of distributing, you just take the x and multiply it by the x to get x squared. and then by the -4 to get -4x. Or if you prefer to see it visually with an area model, one dimension of your area model is just going to have one of the sides is only going to have one box. So then we could do x times x minus 4. So x times x is x squared, and then x times -4 is -4x. So whichever of these ways makes more sense, stick with that. So in standard form, we've got our graph or our equation of x squared minus 4x. Technically, there would be that last term would just be 0, but you do not need to write that down. So x squared minus 4x is good. And then if I look back to our options on the other page, we see that option right here with letter G. All right, we've got 2 more graphs to match. Both of these graphs are unique. I think you guys can figure out why graph 5 is unique. And that's because this is the only one that's opening down. So we have talked about this a little bit. Opening down is going to mean that there's a negative coefficient in front of the x squared term of this equation. So we'll start this the same way we start all of them. We've got -2 and +2 for our x-intercepts. So -2, +2. Then to build the equation in factor form, we would just add this 2 over. So that would generate the factor x plus 2. And the second factor of, since we have the x-intercept of +2, that would generate the factor of x minus 2. But we have talked about the fact that this graph of this parabola opens down means that there is a negative out front of this. So this negative, when we put this in standard form, I'm going to leave the negative out of it at first, but just a reminder that that negative has to be there in order for this to open down. But we can still multiply out the x plus 2 times x minus 2. So that'll give us x times x times 2, x times -2, and then 2 times -2. Okay, so in standard form, I'm going to write it over here first because I know that this negative is out, must be there. And then when I go ahead and simplify the terms inside the area model, we've got x squared. I'm going to put this in parentheses because that negative is going to be applied to the whole thing. So we've got x squared plus 2x minus 2x. So our x terms actually cancel each other out. And then we're just left with -4. So the equation would be negative and then the x squared minus 4. Now you could distribute this through. You could distribute the negative through and it would equal -x squared, and then negative distributed to the -4 would result in +4. So either one of these equations is correct. And then when we go look at our options here, there's only one equation with a negative coefficient in front of the x. So all these others don't have a negative in front. So that means we are obviously choosing D for that. Okay, now this very last one is also different. Again, looking at the shape of this parabola compared to the other 5 we've seen, even compared to this opening down one, this is unique because we can see that it's like skinnier. It looks like someone has, like you've grabbed it from the top and bottom and pulled it. So it does, and we would even call that a vertical stretch. So that graph has been stretched, which means there's going to be something additional to consider with its equation. So the intercepts will still allow us to determine the factors of this. So we've got an intercept at -1/2 and +3/2. So that means we can start our equation. I'm going to leave a little space after the equals sign because when we have a graph that is either upside down, we have that negative out front. If it looks stretched or compressed at all, that means there's some other number or coefficient out front with it. So I'm going to just quickly pause and show you in the same way that when I mentioned this in one of my classes, but let's say I had this line, y equals x plus 1. I know you guys all know that this has a y-intercept of 1, and then there's technically a 1 in front of the x, so a slope of 1 as well. So that is a line with a slope of 1 and a y-intercept of 1. Whoops, sorry. But if I put another number in front of this other than 1, so let's say I put a 5 out front of here, this line still crosses through the y-axis at 1, but that 5 means my graph is going to increase and grow much more quickly because now my slope is 5, not 1. So just like that number out front impacts the steepness of a line, the number out front also impacts, I wouldn't call it steepness anymore with a parabola, but it definitely impacts the stretch or the growth of the parabola. So I'm going to leave a space right in front and at least start with building our factors. So we've got x, if my y-intercept is -1/2, then that will generate the factor of x plus 1/2. And then with the intercept of 3/2, that will generate the factor of x minus 3/2. So don't be nervous about the fractions. We can handle that. So we're going to multiply out x plus 1/2, x minus 3/2. So x times x is x squared, and then we've got 1/2 x, and then -3/2 x. And then when we multiply 1/2 times 3/2, we're just multiplying. Let me zoom in. So we are just multiplying 1 times the -3. And then the denominator is 2 times 2. So we end up with -3/4 there. So combining all of our like terms, our equation in standard form, I'm going to write it out to the side here because we are going to have to figure out one more piece of it. Again, I'm leaving a little space after the equal sign because I know that there's going to be some coefficient that is going to, we'll need to figure out. So that's going to be x squared and then 1/2 x minus 3/2 x. So if I'm just jot this down up here, 1/2 minus 3/2. So that's just going to be 1 minus 3 is -2 halves. So that's just equals -1. So that's my x term. So -1x and then minus 3/4. So it's x squared minus x minus 3/4. So if we go and look at the next page trying to find a graph like that, do this so you guys can see both at the same time. Okay, so we got x squared minus x minus 3/4. So looking at our options, option H, x minus 3 squared, we know that this would have to be a parabola that since it only has one factor that's being squared, it would be just like this one, meaning the vertex would be on the x-axis, which is definitely not the case here. So we can rule out H. And then looking at these other last three options, x squared minus 11x plus 28. So we've already established the fact that there's got to be some coefficient out front of this whole thing. So it's not going to be option C because our x squared term does not have another coefficient other than 1. So then we're down to these last two options, 2x squared plus 11x plus 5, or 4x squared minus 4x minus 3. So even just looking at the signs between plus and minus, the only one this could be would be option I, the very last one. So we see the minus 4x and the minus 3. So those two signs would still have to be consistent. What's different about our option is that instead of x squared, it's 4x squared. Instead of minus x, it's minus 4x. And instead of -3/4, it's minus 3. So what that means is there is this stretch value out front of a 4. And then what they did to get this equation was just distribute that 4 to each of those three terms. So that's why in the end, we end up with this equation of 4x squared minus 4x, and then 4 times -3/4 is just -3. So I wouldn't expect you to generate this all by yourself, looking at it, but we can just use the process of elimination and kind of logic our way through the fact that this last option was the only one that could match with that graph. So on the next page, we're actually going to figure out how do we mathematically figure out what that number out front of a parabola is going to be. So that's what we're going to do in these final two examples. So turn the page and look at 51. We are revisiting the water balloon toss and coming up with a way to figure out the exact equations of these parabolas that could model the path of the water balloons. So this one, we're going to look at the graph. This was the original graph given for Jen's toss. So we want to write an equation for this parabola. So we're going to start just like we started all the other ones. We're going to look at the x-intercepts and use those intercepts to generate our factors. So we'll start there. We know that this is opening down, so we're going to expect a negative at some point, but we're also going to expect some other numbers. So this is a pretty stretched out parabola as well. So starting with our x-intercepts, we've got 0 and 8. So remember that an intercept of 0 would generate the factor x minus 0, which is just x. The second factors with the interception or the x-intercept of 8 would be x minus 8. So we've got our initial equation, factored form of x minus 0. I'm leaving a little space here. X minus 0 is just x times x minus 8. And then just like I had mentioned with that example with the line that I gave, where we put a number out front of a line and that of the x in a line equation, and that means the slope is steeper. We use the letter M for that. For parabolas, we're just going to use the letter A. So we're going to need to find out what that A value is. To do that, this is our equation. We just need to find out what A is. The good news is we have an entire graph of x, y coordinates here that should also work with this equation. So what that means is we can pick a point on this graph to plug in for x and y, and then we can solve for A and figure out what that has to be to perfectly match this parabola. So there are only a handful of points on Jen's graph that cross through at integer values. So this one here at 1, 14, this one here at 2, 24, and then there's a few more, but all we need is 1. So let's just pick the point 1, 14. So I'm going to write that down, and I'm also going to write x and y and label those because it's really easy to get those flip-flopped in this equation. So we know that this point has to work with this equation since we're modeling this, or we're looking for the equation for this exact graph. So all we have to do is plug in 14 for y. We're going to solve for A, and we're plugging 1 in for x. So 1 times 1 minus 8. So we end up with 14 equals 1 times A, that's just A, times 1 minus 8, which is negative 7. Solving for A, just divide by negative 7, and we end up with an A value of 14 over negative 7, which is negative 2. So we were almost done with the problem at this point here. We knew our two intercepts, we generated our two factors, but we still had to figure out this A value. Now that we have the A value of negative 2, our final answer is just going to be rewriting the equation. Instead of y equals ax, it's negative 2x times x minus 8. So this would be the equation in factored form. If we wanted to distribute that, we could do that. And we could distribute the negative 2x to the x and get negative 2x squared. And then negative 2x times negative 8 would be positive 16x. So these are both correct, whether or not you keep it in factored form or multiply it out to standard form. Okay, one more example. So this one was, we were given only a little bit of information about Al's water balloon toss. So for his, we were just told where the balloon started, which was the 10-yard line, where it landed, which was the 16-yard line, and then that height of 27 yards. So if it helps, draw a quick visual. So if we're talking about a graph, it started, he launched it at the 10. So let's say 10 is here, 16 is here, and it reached a height of 27. So that means the vertex is up here at a y value of 27, and the parabola looks like this. So we know that the x coordinate of the parabola of the vertex, we weren't given the x coordinate discretely, but we know that the 10 and the 16, right in the middle of that is 13. So we know that the vertex has to be at 13 comma 27. So just like all the other examples we've been doing, we've got two x-intercepts, one at 10 and one at 16. So working backwards, generating the factor for that. Again, I'm going to put my a value out front because that's something we're going to need to solve for. But we do know our two factors will definitely be x minus 10 and x minus 16. So what we need to do is figure out what that A value is. Unlike Jen's graph, we only have one other point on Al's graph. So we've already used the two x-intercepts to get the factors, which means our only option for an xy pair to plug into our equation and solve for A would be the vertex of 13, comma 27. So we're going to plug in 27 for y. And A, we don't know, we're gonna solve for it, and then 13 in for X. So it'll be 13 minus 10 times 13 minus 16. So we've got 27 equals A, 13 minus 10 is 3, 13 minus 16 is negative 3. So we end up with 27 equals A times 3 times negative 3. That's negative 9A. Then solving for A, we would divide both sides by negative 9. So 27 divided by negative 9 is negative 3. So with an A value of negative 3, it should always make sense. So we look back over at the parabola, it's opening down. Obviously, my graph isn't drawn to scale because 27 is right here when you compare that to my X scale. It's obviously not drawn to scale. This would be much more stretched out. So the negative 3 should make sense. Then again, so we were almost done at this point here. All we needed to do was find that A value. So once you find the A value, you go back and rewrite it as y equals, and now we can actually write the negative 3 out front times x minus 10 times x minus 16. So we don't need to multiply this out at this point. You would just leave it in factored form. It's fine. So that's how you find the full equation of a parabola using the intercepts, not just for parabolas that have that clean cut x value or x squared coefficient of 1, like all of these. So these all had that coefficient of 1. So even other parabolas that have been stretched or even compressed, you guys now have the ability to find the exact A value out front, what we'll call the A value or the stretch value. We're not going to do part C, but we will pick up with problems just like this next class. So I will see you guys then.